Guys, welcome back. So today we'll see about set theory. First we'll start with the definition of set. What is set? So set is a collection of objects. For example, students in the class. So collection of students in a class, or we can also say collection of all natural numbers. And so on, right? So this collection can be like names of the students, right? And we represent the objects. So each of the object is called as element of a set, of this set. So set is represented within this flower braces, and the objects are separated by commas. For example, if we take set of natural numbers, so we can write it as 1, 2, 3 and so on. So we can represent it like this. So if a set of, let's say, players in Indian cricket team. So we can name this, right? So let's start with Rohit Sharma, Shubman Gill, Virat Kohli, and so on until Jasprit Bumrah, right? So we know this, there are only 11 players at any given time, right? But if you see the natural numbers, they are 10 to infinity, they are infinitely many. So these type of sets are called as finite set. So if we take this as set S2 and S1, we represent n of S2, n of S1. So n of S1 tends to infinity and n of S2 is finite. So this is finite set, and this is nothing but infinite set, because the number of elements in the set is infinite. And we can also define something as set of objects inside an empty box. So inside an empty box there is no objects, so we just define it this way. It is an empty set, so this is called an empty set. So as another example, if you take set of beds in a bedroom, so usually we have only one bed, right? Let's say bed 1. So the set has only one element. This type of sets are called as singleton set. And there can be, let's say, two sets, S5 and S6. They are said to be equal if they have same number of elements, same elements in them. So same elements in them, then they are equal sets. For example, we can take S5 is set of natural numbers, so it will be nothing but 1, 2, 3 and so on. And set 6 is whole numbers excluding 0. So this is also again 1, 2, 3 and so on. So this basically the same thing. So we can say S5 is equivalent to S6, right? It is equal set. Also the order in the set doesn't matter. So set of natural numbers we can also write like this. So we can write in any order. Only thing matters is, like, for each element in one set there should be a same element in the other set, right? Only that criteria is enough. And if there are repeating objects, right, 1 1 2 3 4, we can just combine them and write it as single object, because it is basically the same, right? It's like if, say, there is one person called Ram in a class, and his name is supposed repeated twice. Like I'm saying, this is the same person. If it is a different person, then you have to represent it differently, like using their surnames, like Ram S, Ram B, that way. If it is the same person, you can just combine them, and it is equivalent representation. So here 1 and 1 is same. It does not distinguish between numbers, right? So it is equivalent to writing it this way. So this is called as equal set. So two sets are said to be equivalent if they have same number of elements. So only the n of S1 and n of S2 matters, right? S1 itself need not be equal to S2. This is not necessary. So the equal to is not necessary. This is only necessary for equal set. Okay. So next we will see about subsets. So with the word itself we can find what is the meaning, right? Suppose if we have, this is S1, if S2 is something like 2, 4, 5. If you see that the elements of S2 is contained in the elements of S1. So S2 is contained in S1. So we say S2 is a subset of S1. So this symbol is subset. If we write this way, it means it is either subset or equal. So it's like either or, right? So anyone, it may be equal, or otherwise it's just a subset of S1. So at minimum it is subset, and at a very strict condition it is a equal. Okay. So if we have S2 is equal to 1, 2, 3, 4, 5, then we can say S2 is a subset or equal to S1. And in this case we can also say S1 is a subset or equal to S2. So these both implies S1 is equal to S2, right? So both these conditions should be satisfied to arrive at this condition. Okay. So if a given set, let's say S1, has n elements, then we ask the question, how many subsets are possible? Okay, so how many subsets are possible? So we'll go one by one, right? Let's say X is the, let's say Si are the subsets. So S1I are the subsets of Si having I elements. Okay, so S10. So this is just the empty set. So this is also a subset. So empty set is subset of every set, right? So this is always 2. And then S11, if you have one element, right? How much possibility? So there are n elements. So each element can be occurring once. So it is n times. So next we'll see about, like, also in the upcoming lectures we'll see about combinations and permutations. So this is equivalent to saying out of n elements I pick one. So this is combination. We'll see it in the upcoming lectures, but for now take it as granted. And then S12, having each subset is having two elements. This is nothing but out of n we select 2. So how many possible ways it is there? So like that we'll have up to S1n, and it will be NCn. So from n we are selecting all the n. This is of course equal to 1. So the sum of all of this will be the number of subsets, right? So number of subsets, I'll write it down. So this is equal to, this is nothing but NC0, selecting none. So NC0 plus NC1 plus NC2 and so on up to NCn. So we'll see that this sum will be equal to 2 power n. Okay. So there are 2 power n subsets possible. Other way to see it, right? There are n elements. So if we take any set, for each of the n element, right? 1, 2, 3. Let's say these are the n elements. Let's say x1, x2, x3. These are the n elements. For each of this, we can either choose to include this in the set or not include. So there are two possibilities for each. So for n, it will be 2 into 2 into n times, which is nothing but 2 power n. So number of subsets is 2 power n. Then we define something called as proper subset. Proper subset is all subsets excluding the original set. So the original set was containing n elements, right? So that is also a subset of that. So proper subset is we are excluding that. So this thing comes, right? S1, S2. So this equal to, if we remove that. So if it is strictly just a subset, then it is called as proper subset. If that equal to comes, then it is not a proper subset. So number of proper subsets will be 2 power n minus 1. That 1, the subset, the set itself we are excluding. Okay. So next we'll see some laws. So the first one is the commutative law. So before this, I need to explain you two things. 3 things actually. The first one is, let's say there are set A and B. Okay. So these will fall under something. So these will be subset of something. So the upper set, the uppermost set containing all elements under consideration, the biggest set containing all elements under consideration, under our consideration only. So if we are working with natural numbers, then natural numbers will be this U. So what is this U? Is called the universal set. And from this we are taking some A and B. Then we can define something called as A union B. So what is A union B? So this, let's say this is some set S. Then S contains elements present in A or B. So if it is, the element is present in A or B, then all the elements will be present in S. For example, if A is 1, 2 and B is 2, 3, then S equal to A union B will be 1, 2, 3. So from A it has 1 and 2, and from B it has 2 and 3. So this is union of set. The third thing is intersection. So we represent it by this symbol, the inverter U. Let's say this is again some S. Then S contains elements present in both A and B. Okay, so it should be present in A and B. So for the same example, A intersection B will be just 2, right? Because only 2 is common to both A and B. So this is union and intersection and the universal set. Okay. So first thing is commutative law. What it says is A union B is equal to B union A. So if you interchange also, it's going to remain same. So from common sense also we can see it, right? So similarly for A intersection B is same as B intersection A. The second law is associative law. So here we have A union B union C is equal to A union B union C. So when you have 3 unions, we can take either the first 2 first and then do it with the third, or take the second and third first and then do it with the first. So the result will be same. Similarly for intersection, A intersection B intersection C is equal to A intersection of B intersection C. So the third law is distributive law. So here what we have is, if we have A intersection B union C, then it is equivalent to saying A intersection of B union A intersection of C. Okay, and if we have A union B intersection C, then we have A union B intersection A union C. So this union just distributes over the intersection that way. Then we have identity law. Here what we have is A intersection A is nothing but A, right? Again A union A is again A, and A intersection U, the universal set. So universal set contains everything, and we are intersecting with A, it will still be equal to A, right? Okay, then we have the complement laws. So here what we have is, if A complement we define as U minus A. So everything in the universal set except A, that is what this symbol says. So this is A complement. If we have A intersection A complement, you see they don't have any elements in common because they're complement of each other. So this will be equal to 0 set. So 0 set, this is nothing but 0 set or the empty set. It is represented by 5, let's say. And A union A complement. So this will include all the elements in the universal set, right? So this will be equal to U. Okay. And finally we have the De Morgan's law. This is again like distributive law, but it is with the complement. If we have A union B, the whole complement, then it is equivalent to saying it as A complement intersection B complement. So you can see A and B have become complement and union has reversed to intersection. Similarly, you can guess what it will be for A intersection B complement. It will be A complement union of B complement. So there is some easy way to visualize this. So that is called as Venn diagrams. So in Venn diagrams we have a rectangle. So everything inside this represents the universal set U. Okay. Then if we draw two circles, one circle, let's say this is set A, it contains some elements in A. Then let's say this is another set B, right? And this is the universal set. So using this Venn diagram, it will be easy for us to prove these laws, okay, to visualize also. So usually when solving in exam questions in exams, we just directly can use the Venn diagrams to visualize and solve the questions easily. Okay, so we have A union B. What is A union B? This is A, this is B. So union will be all the elements in A and B, right? So that will be same as B union A, correct? So this is same. So I'll just copy this so I can use it repeatedly. So this is for union, right? What about intersection? What about intersection? A intersection B is this part, which is common to both A and B, right? And B intersection A is same. Okay. So then what we have? So here we have 3, right? So we need to draw another circle. So this is some C. So the first one is A union B union C. So first we are doing A union B. So what will be A union B? This entire, right? And then we are doing the union with C. So it will include all these. Okay? And other way if we do it. So what is the other way? B union C. So this is B and this is C. And then we are taking union with A. So you see both these are equal, right? Similarly for intersection also you can prove. You will get this middle region. Okay. And then we are coming to the distributive law. So in distributive law, what do we have? A intersection of B union C. So first we have B union C. So this is B union C. And then we are intersecting it with A. So it will just be this part. Okay. Right? So we are saying that is equal to A intersection B. So what is A intersection B? This part. Union of A intersection C. What is A intersection C? This part. And their union is same, right? So you see, here also it is the same. Here also it is the same. So they are equal. Similarly for this also you can try it out. And the identity laws are easy, right? If we have A and U, A intersection A will give again A. A union A will be again A. And A intersection with the union. This circle intersected with the rectangle. It will give only this part, which is nothing but A itself. And complement law. So if we have this U and A, so this is A, right? And this entire outside portion, excluding the circle inside the rectangle, will be A complement. Okay? So that is what it means. And A intersection A complement, you can see there is no intersection. So it is an empty set. And A union A complement, it is the entire rectangle, which is nothing but the universal set. So this is for this. And then we have the De Morgan's law. Okay. So we have two circles, A and B, and we have U, and A union B complement. So what is A union B? This is A union B, and we need complement of those. So it will be this entire region, the black I am shading. So now let's see the right hand side. So A and B, A complement. What is A complement? This entire red, right? Okay. And what is B complement? So excluding B, everything, right? And they're saying A complement intersection B complement. Okay. So if you see inside A and inside B, there is only B complement, A complement separately. So their intersection will be 0. So the intersection will be only in this region. Hence, this is equal to this, right? So this equality holds. Similarly, you can try to prove for this one as well. So finally, let's now see some two important formulas that we will be using often. So the first formula is n of A union B. So it is the number of elements in A union B. So this is equal to n of A plus n of B minus n of A intersection B. So how do we visualize it? So we have A, B and U. So on the left hand side we have this entire thing, right? Okay. So what do we have on the right hand side? So n of A is nothing but this entire thing, correct? And n of B is number of elements here. But in the left hand side, if you see, the middle part is counted only once, right? So just to not confuse you, I'll just put the left hand side in the left and right hand side in the right. Okay. So if you see, this middle portion is counted only once when we are doing A union B. But on the right hand side, if you see, n of A plus n of B, we are counting the center part twice. So we need to subtract that once. And what is that center part? It is nothing but A intersection B, right? So this one we are subtracting. Okay, so this is n of A union B is equal to n of A plus n of B minus n of A intersection B. So this is one important formula. So this can be asked in many cases and many examples. There's more recurring question. And another version of this is with 3 sets. So n of A union B union C. So for this one, this is again also mostly they ask these kind of questions to increase the level of difficulty. So this is given by n of A plus n of B plus n of C. So all the single terms A, B, C are in addition. Then similar to this, all the double terms are in subtraction. N of A intersection B minus N of B intersection C minus N of C intersection A plus, so all double terms are in subtraction, and the triple term, here there is triple term possible, right? That will be in addition again. A intersection B intersection C. So if you see on the left hand side there is union, and right hand side there is the single terms and then intersection of two or more terms. So this also can be easily proved using Venn diagrams. So let's do that. So this is U, A, B and C. So left hand side is what we have, A union B union C, which is nothing but all of this taken at once. Okay, on the right hand side, let's see what is there. So we have n of a. I'll just put a small one. So n of a, right? This is on n of a. Okay, and then n of b. So n of b will be this one. If you see now itself, this portion is being counted twice, correct? Okay, then we'll do n of c. So this is b and c. N of c. So n of c will include this. Now from these three itself, if you see, this middle portion, right, is being repeated twice. So between a and b, this portion is repeated twice. Between a and c, this portion is repeated twice. And between b and c, this portion is repeated twice, correct? Okay, so this I'll just maybe I can shade it separately. I'll shade it for you separately. Okay, so this one came once, this region also once, this is once. If you see, these regions are repeated twice. And what about the middle region? It is repeated thrice. We finally want such that all the regions are counted only once, right? Okay, so now what we are doing, we are subtracting this, whichever came 2, right? We are trying to subtract those regions. So we will be subtracting these regions. This is A intersection B. And B intersection C. And C intersection A. So this is n of A plus n of B plus n of C. And we are minus n of A intersection B minus n of A intersection, B intersection C minus n of A intersection C or C intersection A. Both are equal because of commutative property. Yes. So here if you see, this is again getting subtracted thrice. So we are achieving this getting subtracted once. This regions getting subtracted once. So we have 2 minus 1, 2 minus 1, 2 minus 1, which is nothing but 1 itself. But if you see the center portion, it becomes 3 minus 3, 0. But we need to count the center portion also once, right? To match it with the left hand side. So what we do, we just add that finally. So this is just the center portion, which is nothing but plus n of A intersection B intersection C. So now all becomes equal to 1. So we can say left hand side is equal to right hand side. So these two formulas are very important to know for quick solving in the examination. Alright guys, that's all for today. Stay tuned for more. Thank you.